We're going to talk about matrix operations, and this is very similar to the vector operations that we talked about in the earlier video, but there is matrix addition, and it works just like the vector addition. I'm going to add, let's add A plus B, and in order to add two matrices, they have to be the exact same size. So both of these matrices are 2 by 3. So A is 4, -1, 0, 3, 5, 2, and B is 1, 3, 1, 5, 1, 7. And we're going to add the corresponding entries. So the top left corner of, we would say the 1, 1 entry, right, is going to be 4 plus 1, so that'll be 5. Right, so we're just going to add the corresponding entries. The 1, 2 entry is 0 plus 1. The 1, 3 entry is 5 plus 1. The 2, 1 entry is -1 plus 3. And the 2, 2 entry is 3 plus 5, which is 8. And then the 2, 3 entry is 2 plus 7. So we get 5, 2, 1, 8, 6, 9 is the sum. And so that worked just like vector addition. You could not add, say, A and C together because they're not the same size. And we also have scalar multiplication. Again, it's just like vector scalar multiplication. If I multiply C times 3, I'm going to multiply everything inside the matrix by 3. It's just going to scale all the columns. So this would be 6, 0, -9, 3. So it started out as 2, 0, -3, 1, and it gets scaled up to 6, 0, -9, and 3. So that's pretty easy. Matrix multiplication is going to be a little bit more difficult, but again, it's very similar to vector, a matrix times a vector. Remember that vector was just a matrix that had only one column or one row. So now we just have multiple columns in our matrix to deal with. So we're going to multiply A times B, and we're going to do it two different ways. So the first way is by doing matrix vector products. So I've got 2, 1, 3, -5 times 4, 1, 3, -2, 6, 3. A is a 2 by 2 matrix, and B is a 2 by 3 matrix. The number of columns of A has to match the number of rows of B in order to be able to multiply these. So these match. That means we can actually do the multiplication. So what I'm going to do is multiply A times each column of B. Okay. And what I get, the product is going to be a 2 by 3 matrix. So the 1, 1 entry is going to be, or let's say the first column is going to be this matrix A times the column 4, 1. When you do a matrix times a vector, you multiply each entry of the vector times the column. So it's going to be 4 times 2, 1. So it'll be 8, 4 plus 1 times the second column, that'll be 3, -5. So it's going to be 8 plus 3 is 11. 4 minus 5 is -1. Right, so for the second column, we're going to multiply A times the second column. We're going to do the same thing. So 3 times the first column of A plus -2 times the second column of A. So I've got 6 and 3 plus -6, +10. So it's going to be 6 and -6, that's 0. And we have 3 and +10, it's going to be 13. And then for the last column, we're going to multiply the matrix A times the last column, 6, 3. And I'm going to multiply 6 times the first column and 3 times the second column of A and add those together. So I've got 12 and 6, and this would be 9 and -15. So 12 and 9 is 21. And I've got 6 and -15. That is -9. All right, so if you followed along with that, then you probably realize that we can just do our dot product method. So we had a dot product method for multiplying matrices, and we can do that again. And we're going to end up doing the same operations here. So now I'm going to think about this entry. The 1, 1 entry is the first row of A dotted with the first column of B. So that's 8 plus 3, it's 11. And then the 1, 2 entry is the first row dotted with the second column. All right, so we're just going to do that again. So that'll be 6 minus 6, 0. And then we'll do it for the third column. We'll take the first row, dot product with the third column. We get 12 and 9, that's 21. Then for the second row of the product, we're going to dot product the second row of A with each column of B. So the first one is 4 plus -5, that's -1. Second column, 3 and 10, it's 13. And then 6 and -15, it's -9. All right, what about B times A? So B here is a 2 by 3, and A is a 2 by 2, and these two things don't match. So you can't even do this multiplication. So that's something to remember about matrix multiplication, is it does matter what order you multiply in. So regular multiplication, real numbers, it doesn't matter. 3 times 2 is the same as 2 times 3. Doesn't matter what order you multiply them in. That's called the commutative property. Matrix multiplication is generally not commutative. It does happen sometimes, but it's not a general rule that you can follow. And in this case, you can't even do the other multiplication. You can't multiply B times A because the dimensions don't match. All right, let's try A times the identity matrix and see what happens. So A is 2, 1, 3, -5, and it's 2 by 2. So the identity matrix has got to have the same number of rows as A has columns. So it's got to be a 2 by 2 matrix. Identity matrices are always square. So that's a 1, 0, 0, 1 matrix. And let's see what we get. So I'm going to do dot products. So the 1, 1 entry is going to be the first row dotted with the first column. So I got 2 plus 0, so I get 2. And then the 1, 2 entry, first row dotted with second column, I get 0 plus 3. And then the 2, 1 entry is going to be the second row, first column, 1 plus 0. And then the 2, 2 entry is second row dotted with second column, So 0 and -5 is -5. So we see that this is just equal to A. And that's true for identity matrices. They are the multiplicative identity for matrices. It's like multiplying by 1. So A times I is the same as I times A, and they're both equal to A. So either way you multiply that, you're going to get A. The identity matrix is like multiplying a matrix by 1. Okay. All right, the transpose of a matrix is when you take the rows of a matrix and make them the columns of the new matrix of the transpose. And also taking the columns and turning them into rows. You're just going to switch the rows and columns. So A has a row AB, so that's going to be my first column. My first column is going to be AB. And the second row is CD, so the second column is going to be CD. And you can also think about it in terms of columns and row. My first column of A, AC, becomes the first row of A transpose. And the second column, BD, becomes the second row, BD. So let's just quickly do B transpose. It's a 3 by 2. So B transpose will be a 2 by 3. Those things are going to switch around. So I've got a row that's -5, 2. So that's going to be a column in the transpose. And I've got row 1, -3. So I've got a column 1, -3 in the transpose. And row 0, 4, it's going to be my last column 0, 4 in the transpose. So C transpose, this is a 2 by 4 matrix. This is going to be a 4 by 2. So this row of all ones, the first row is going to be my first column of the transpose. And my second row is going to be the second column. And just notice, let's just look at this one here in B. This is in the 2, 1 position. So in the transpose, it's going to be in the 1, 2 position. So those two things switch. The row and the column of each entry gets switched around.